Einstein was right about almost everything. Special relativity, general relativity, the photoelectric effect that won him the Nobel Prize, mass and energy being two faces of the same coin. The man reshaped the entire universe with a pencil and a notebook. And when he looked at quantum mechanics, at this strange new theory bubbling up in the 1920s, he said something very reasonable. He said, "This cannot be the final answer. There must be something deeper underneath, something we haven't found yet, something that actually makes sense." And you know what? Every serious physicist at the time nodded along because it sounded perfectly logical. He was dead wrong, and I can show you exactly why. See, Einstein had a specific objection. It wasn't vague. It wasn't philosophical hand-waving. The man wrote papers about it. He argued with Niels Bohr about it for decades, and his complaint boiled down to this: quantum mechanics says that certain things in nature are genuinely random, not random because we're ignorant, not random because our instruments are crude, random in principle, fundamentally, irreducibly, as if the universe itself rolls dice before deciding what happens next. And Einstein could not stomach that. He had this famous line. He said, "God does not play dice with the universe." Beautiful sentence, very quotable. And I understand why he felt that way. Every great theory before quantum mechanics was deterministic. You set up the initial conditions, you know the laws, you crank the math, and out comes the answer. Newtonian gravity works like that. Electromagnetism works like that. Even Einstein's own general relativity works like that. You tell me the shape of space-time and the distribution of matter, and I can tell you exactly what happens next. No ambiguity, no dice. So, when quantum mechanics showed up and said, "Actually, we can only tell you the probability of what happens next," Einstein treated it the way a master watchmaker would treat someone claiming his finest clock runs on wishes. He respected the math. He acknowledged the experimental predictions were accurate, but he believed deeply that quantum mechanics was incomplete, that somewhere underneath all those probability calculations there were hidden gears turning, hidden variables, real definite properties that particles actually possess at all times, and we just haven't figured out how to see them yet. This wasn't a fringe position. This was Albert Einstein, and his argument was sharp. In 1935, Einstein published a paper with two colleagues, Boris Podolsky and Nathan Rosen. The initials gave it a catchy name, the EPR paper, and the argument went like this: quantum mechanics says that two particles can be entangled, meaning their properties are correlated. You measure one, and instantly you know something about the other, no matter how far apart they are. Could be across the room, could be across the galaxy. The moment you measure particle A, the outcome for particle B is determined. Einstein said, "That's absurd. That would mean information travels faster than light. That would violate relativity, my relativity." He called it spooky action at a distance, and he meant it as an insult. His conclusion was elegant and seemingly airtight. The particles must have carried definite values with them all along, like two gloves packed in separate boxes. You open one box and find a left glove. You instantly know the other box has a right glove. No spookiness needed. The answer was there before you looked. Quantum mechanics just didn't know how to describe it yet. For 30 years, that argument sat there looking pretty reasonable. A lot of people found it persuasive. Even physicists who used quantum mechanics every day sometimes wondered if Einstein might be onto something. But there was a problem. A quiet, devastating problem that almost nobody noticed at first. See, Einstein's argument assumed something. It assumed that if the particles carry hidden values, those values would behave like ordinary classical properties, definite, local, independent of how you choose to measure them. That sounds so obvious it barely seems like an assumption. Of course, a particle's property doesn't change depending on what question you decide to ask about a completely different particle far away. That would be insane. Except nature turned out to be exactly that insane. In 1964, a physicist named John Bell did something brilliant. He took Einstein's assumption about hidden variables and turned it into a mathematical prediction. He said, if Einstein is right, if particles really do carry hidden values that determine all their outcomes in advance, then the correlations you measure between entangled particles must obey a specific inequality, a ceiling. The numbers cannot exceed a certain bound. But if quantum mechanics is right, if the randomness is truly fundamental and the particles genuinely don't have definite values until measured, then the correlations can exceed that bound. They can break through the ceiling. Bell gave us a test, not philosophy, not interpretation, a real experimental numerical test. Measure the correlations, check the numbers, see which prediction wins. And this is what made Bell's work so devastating. It wasn't an opinion. It wasn't a competing interpretation you could wave away with clever words. It was a boundary line drawn by pure mathematics. If the universe operates the way Einstein insisted, the correlations between entangled particles stay below this line, period. No exceptions. But if quantum mechanics is right, if the randomness goes all the way down, the correlations blow past that line like it isn't even there. You can't debate a number. You can only measure and find out. And here's where I come into this story. Because while Bell was working out his theorem, I was neck deep in something called quantum electrodynamics, QED. And QED forced me to confront exactly the issue Einstein was worried about, but from a completely different angle. When I developed the path integral formulation, I had to take seriously an idea that sounds absolutely crazy. A particle going from point A to point B doesn't take one path. It takes every path simultaneously. It goes left and right. It goes up and down. It loops around the moon and comes back. Every conceivable trajectory contributes to the final answer. You add up all of them, weighted by their quantum phases, and the ones that are wildly improbable cancel each other out. What survives, what's left, is the behavior we actually observe. Now sit with that for a moment. Because if Einstein were right, if particles secretly had definite positions and momenta at all times, then the path integral would be a convenient fiction, a mathematical trick that happens to give the right answer. But it's not a trick. It's the only formulation of quantum mechanics where you can successfully combine it with special relativity. It's the foundation of quantum field theory. Every Feynman diagram I ever drew is a picture of this sum over paths. And those diagrams don't describe hidden particles sneaking along secret trajectories. They describe amplitudes, possibilities, all of them happening at once until the moment of measurement collapses them into a single outcome. There's no hidden gear underneath selecting the real path. The superposition of all paths is the reality. The probability isn't covering up our ignorance. The probability is the deepest description we've got. And QED, this theory built entirely on quantum probability, turned out to be the most accurate theory in the history of physics. We calculated the magnetic moment of the electron. The prediction matched experiment to better than 10 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. No hidden variable theory has ever come close to that precision, not even in the same universe of precision. So I had this peculiar situation. The greatest physicist of the 20th century was telling me the foundation of my theory must be incomplete, and my theory was agreeing with experiment to 10 parts in a billion. Something had to give, and it wasn't going to be the experiments. The real blows came in the 1980s. A French physicist named Alain Aspect ran the experiment Bell had proposed. He measured entangled photons. He checked the correlations, and the results violated Bell's inequality. They broke through Einstein's ceiling, not by a little, by a lot, exactly as quantum mechanics predicted. What made Aspect's experiment especially convincing was the timing. He introduced random switching of the measurement settings while the photons were already in flight. The detectors changed their minds, so to speak, after the particles had left the source. There was no way for one particle to send a signal to the other saying, "Hey, they're going to measure me this way, you'd better adjust." The correlations were still there, still violating Bell's inequality, still thumbing their nose at Einstein's perfectly reasonable assumption. The particles were not carrying hidden values. Einstein's elegant glove-in-a-box analogy was wrong. Opening one box didn't just reveal information that was already there. The act of measurement on one particle genuinely influenced what could be said about the other. Nature really is that strange. Let me be honest about what Einstein got wrong, because it's subtle and it matters. He didn't get the physics wrong. His mathematics in the EPR paper was correct. His reasoning was logically valid. What he got wrong was the premise. He assumed that a complete description of reality must look like what we'd seen before. Definite properties, existing independently, behaving locally. He assumed nature had to make sense in the way classical physics made sense, and nature said no. That's the part people miss. Einstein wasn't making a stupid mistake. He was making a profound one. He was insisting that the universe owed him a certain kind of explanation, a deterministic, local, realistic explanation, and the universe just doesn't work that way. I'll tell you what I find most interesting about all this. It's not that Einstein was wrong. Brilliant people are wrong all the time. That's how science works. What fascinates me is the specific flavor of wrongness. Einstein's instinct said, if a theory only gives you probabilities, it must be missing something. My experience with QED told me the opposite. The probabilities aren't a gap in the theory. They're the theory. They're not a veil hiding the real answer. They are the real answer. Think about what that means for a moment. In classical physics, when you say there's a 50% chance of rain, you mean you don't have enough information. If you knew the position and velocity of every air molecule, you could predict exactly when and where every raindrop falls. The probability is about you, about your ignorance. In quantum mechanics, the probability is about the world. An electron approaching a barrier has a 30% chance of tunneling through. That's not because we don't know enough. If you had every piece of information the universe permits, you would still get 30%. The universe itself hasn't decided yet. It decides at the moment of interaction. And no amount of cleverness, no hidden variable theory, no deeper layer of reality can improve on that answer. We know this because of Bell's theorem and the experiments that confirmed it. Einstein spent the last 25 years of his life looking for a unified field theory that would restore determinism. He never found it. Not because he wasn't smart enough, because it isn't there. And look, I say this with tremendous respect. Without Einstein, quantum mechanics wouldn't exist. He's the one who proposed light quanta in 1905. He's the one who showed energy comes in packets. He lit the fuse. He just didn't like the explosion. There's a lesson in that for anyone who does science. Your deepest intuitions about how the universe should work are not evidence for how it does work. The universe is not obligated to match your expectations. And when it doesn't, when the experiments tell you something that feels wrong, something that makes your stomach turn, your job is to listen, not to argue, not to insist there must be hidden gears. To listen. I think the most honest thing I ever said about quantum mechanics was that nobody understands it. And I meant that in a very specific way. I didn't mean we can't calculate with it. We calculate beautifully. I didn't mean we can't make predictions. Our predictions are the most precise in all of science. I meant that the human brain, trained by millions of years of evolution in a classical world, does not have the vocabulary or the intuition to truly picture what's happening at the quantum level, and wanting to picture it, needing it to feel like gears and gloves and billiard balls. That need is what trapped Einstein. He wanted quantum mechanics to feel like classical physics. And I think the deepest lesson of the 20th century is that it never will. Not because we're not clever enough, because reality at the smallest scales plays by different rules than reality at our scale. And those rules involve probabilities that are not masks for ignorance. They are the bedrock. Einstein saw farther than almost anyone who ever lived. But on this one question, on whether God plays dice, he looked at the evidence and said no, when the answer was yes. The dice are real. The randomness is fundamental. And no amount of genius changes that. So let me leave you with something to chew on. If the deepest layer of reality is genuinely probabilistic, if the universe truly doesn't decide until the moment of interaction, then what does that say about the nature of existence itself? Is an electron that hasn't been measured even a thing? Or is it something else entirely, something we don't have a word for? Tell me what you think. I'd like to know.